Okay, hi everyone. In this lecture we're going to talk about diode rectifiers, and particularly in single phase diode rectifiers. Okay, so diode rectifiers. There are basically two types. Of single phase diode rectifiers. One is basically namely single phase half wave rectifier and single phase full wave rectifier. So let's assume we have an AC source and then we want to rectify it, and we want to use diodes in order to do that. So let's say we have an AC source and then we want to rectify this. How can we do this? One way is to just add a diode here, and then let's say our load here is a resistor. Okay, and so this is our Vs being equal to Vm sine of omega t, and let's call this R, and then the voltage across R is V out, and let's say the voltage across the diode would be Vd, and I have my I out as the current through my load. Okay, so this is capital M. So this is called a half wave rectifier. Why do we call it half wave? Because if we draw its voltage waveforms, so let's draw the Vs first. Okay. Okay. So I'm going to try to draw a sinusoidal voltage now. See, this is pi over 2. This is pi. 3 pi over 2, and then this is 2 pi. And I'll draw Vm here. Then minus Vm here. Okay, so let's say we have our Vs voltage like this, and oops. Okay, so let's draw another graph. let's try to draw a line. Okay, never mind, let's just try it with hand. Okay, so now I want, so this was VS. Okay, so this was VS. And now for V of out, my V out, because I have a diode here, only conducts when we are in the positive half cycle, so it would be equal to Vs and then it would be equal to 0 for the rest of the cycle. And so let's draw another graph. So my I out would be again the same thing. So half sinusoidal here, and then for the rest of the interval it would be 0, and here I would have Vm divided by R, and for my Vd, so it would be 0 when the diode is conducting, and it would be negative the source voltage. So the maximum current, the reverse current that is applied to the diode would be equal to minus Vm actually. Okay, so this was for the half wave, and so let's look at the waveforms for the single phase for the full wave rectifier. So this is going to be the circuit for a full wave rectifier using a diode bridge. Okay, so Vs again is equal to Vm sine of omega t, and so this would be I out, this would be R, this would be V out. Okay, so this right here is called a diode bridge rectifier. So these four diodes constitute a diode bridge rectifier. D1, D2, D2, D3, and D4. Okay, so let's draw the graphs for the full bridge rectifier in comparison to the half bridge. Okay, so we'll do the same thing that we did before. Maybe I'll use this little ruler here. Okay. And so we'll do the same thing for Vs now. Vs I'm gonna try to restart this because this doesn't seem to be working well. Okay, so I restarted OneNote, so hopefully it will work well from now. Okay, so Vs, and then Vs is a sinusoidal with a peak amplitude of V of m, right? So something like this. So the same thing that we had here. And then V out this time would be V out would be a rectification. So this was a half cycle rectification, and it was able to just only, as you can see here, only rectify half cycle of the whole Vs here. So now what we'll see is that we can do a full wave rectification. So if this is Vm, so we would have again the negative half cycle of Vs would also be rectified. Okay, so V of out, now here we want to see I of out. I of out would have the same kind of characteristics as V of out because the load is a resistive load. And so here we know that in this situation D1 and D4 conducts, right? So this diode here and this diode here conduct because the positive current goes through this diode and continues its way and goes through the resistor, goes back through the diode, and makes its way back. Right? And in the negative cycle where we have a negative voltage, we would have D3 and D2 on. So when we have a negative voltage, so the current here would go from like this, and then D2 back to D3, and it makes its way back because the negative voltage here forward biases this D3 because the voltage here would be higher than the voltage at the other side. Okay, now let's look at the before we do that, let me just copy this and then paste one more. Okay. So the voltage of diode 1 and V of diode 4. So because in the first interval the diodes don't conduct D1 and D4 here, therefore the voltage would be 0, and when they don't conduct it will be minus Vs, something like this. Okay, and will be kind of similar for D2 and D3 as well. So VD2 and VD3. So it would have bring this further down. So something like this here. Okay, so let's look at the half wave and full wave rectifier. So the half wave rectifier, as you can see here, the difference. So the output voltage only rectifies half of the cycle, line cycle, whereas in the full wave, it rectifies both the half cycles, the negative and the positive half cycle. And that's the main difference. So now let's look at some of its performance parameters. So let's look at the average voltage, or the DC voltage. So the DC voltage of the output. So V out average over one line cycle basically would be VDC, and we're basically finding the average voltage of this graph here. So we covered how we can find average and RMS values, so I'm just gonna write the end answer for these values. So this would be Vm divided by pi, 0.318 Vm, and the average voltage for this part would be again VDC. The DC voltage would be for the full wave, where we are actually taking an average over this, would be 2 Vm divided by pi, which is 0.636 Vm. So some of the other important things that we can look at is the RMS voltage. So the RMS voltage here of the V out RMS is equal to Vm divided by 2, or half of Vm, and for full wave rectifier, V out RMS is equal to Vm divided by root square of 2, which is what we expect, because the RMS of a full wave rectified would be equal to the RMS of actual sinusoidal, which is Vm divided by root square of 2, 0.707 Vm. Okay, so what else is important? So maybe the average current, we want to look at the average current here. So the average current would be the IDC, and then IDC would be VDC over R. Right, so it would be equal to 0.318 Vm divided by R, and the average I out here would be, again, IDC would be VDC divided by R, which would be 0.636 Vm divided by R. Okay, so yeah. Okay, now so let's introduce some definitions, and then we'll come back and say what those definitions are for each of these, the half wave and the full wave rectification. So first is the rectification ratio. Rectification ratio is basically a figure of merit for comparison of the effectiveness of rectifier, and it can be basically written as PDC over P of L, which is VDC IDC divided by V out RMS I out RMS. Okay, so let's find this for half wave. For half wave it would be PDC over PDC IDC over V out RMS I out RMS. So that would be 0.38 multiplied by 0.38 Vm squared divided by R. So we would have this to the power of 2. And then we would have V out RMS, which is 0.5. And then I out RMS where we didn't define. So let's define I out RMS first and then look at this. So I out RMS here basically is the same thing, V out RMS over R, which is 0.5 Vm divided by R. So the rectification ratio is equal to VDC IDC divided by V out RMS I out RMS, and the end answer for this would be 40.5 when we substitute these values from up here, these 4 values that we found. And for the full wave rectifier would be equal to VDC IDC divided by V out RMS I out RMS, which is equal to 81%. So as you can see, in full wave rectifier, because we are utilizing both sides and therefore our V out is not 0 for half of the cycle, like in this situation, we would have a better rectification ratio. Okay. Okay, next is form factor. Which is basically this. Form factor is equal to V out RMS divided by VDC. Okay, so form factor here would equal V out RMS divided by VDC 0.5 Vm divided by 0.318 Vm, which would be equal to 1.57. And then form factor for full wave is 1.11. So another definition that we have is the ripple factor, which we can define as the ripple factor can be defined as VAC RMS, which is basically the effective RMS of the AC voltage, AC component of the load, divided by VDC. So this is the effective AC, basically RMS value. So I think RMS value of load voltage. So VAC can be written as V out RMS to the power of 2 minus VDC to the power of 2. Okay, so the ripple factor for half wave, if we put this in here, we can simplify it further as being equal to ripple factor being equal to form factor to the power of 2 minus 1. So for here, I can write form factor to the power of 2 minus 1, which is equal to 1.21 here, and for full wave is equal to 0. So form factor to the power of 2 minus 1, which is equal to 0.482. So I write P here, this is S. Okay. And then the last one would be the utilization factor of the source. Which can be, the utilization factor can be written as PDC over Vs RMS, which is the input. Vs was the input voltage, and Is RMS, which is the input RMS current. Did we define Is here? Oh, we didn't. So okay, Is is here, and Is is here. Okay, so the utilization factor, basically how well we are utilizing the source. Obviously, we expect a low value for the half wave and then a higher value for the full wave. So for the half wave, we have VDC, IDC divided by VSI, V out IR. This is VDC, IDC divided by VSRMS, ISRMS. For the half wave, if we calculate this, we'll have 0.286. And for the full wave, if we calculate the same thing, we would get 0.81, which is much better. So what this means is that basically if we want to, from here 0.286, so if we want to deliver 1 watt of power here, 1 watt of power here, we're going to need basically 3.496 volt ampere from our source in order to provide only 1 watt here. That's very poor utilization of our source. But in as our utilization factor goes up, also basically we would need less volt ampere from the source in order to provide the same amount of power. Okay.